Alrighty, let's get started. Welcome to week 3 of the IEEE PCB design workshop. Today we're actually going to start our PCB layout, which is probably something you're going to spend a lot of time doing. This is one of the more difficult aspects of PCB design after you get your design basically finalized, because this is what's actually going to get physically manufactured. So just for a brief review, this is our workshop. We're on week 3, which is an introduction to PCB layout. The final design files that, if you want to submit your own design to get manufactured, will be around October 1st. So I'm going to set the cutoff to October 2nd, which is after that workshop, just so you know. But I'll send out more reminders as that gets closer to us. Just a reminder about some announcements. ASUU, we're still waiting on a request. We should hear back probably October-ish. I'm going to be emailing them just to see what the status is probably tonight, see what they have. And also, if you're doing any alternative projects, your submission deadline is the same as everyone else, but you're just limited to 10 by 10 centimeters for JLC PCB. I will shill once again. FSAE is doing our electric race car. We have our tractive meeting directly after this workshop. I think today we're going to go over board reviews, so if you'd like to see some actual boards that are finished and are part of the club, today would be a good day to check that out. There's a Discord link, but I presume many of you have already seen this before. And then there's also the IEEE Discord, which I don't really need to shill anymore. So any questions before I start today? I think we're good. So first thing I'm going to go over is just like, what's a printed circuit board, just so people know what it is. PCBs are basically a stack of conductive and non-conductive layers used to connect electrical components in a circuit. So this is the most common type of electrical assembly just because it's so easy to manufacture, and it's a standardized way that people have basically gone to. There's old techniques such as wire wrapping, there's dead bug style for prototyping. Breadboards are a good way to prototype, but PCBs are basically what gets put into every product. Components can be placed on both sides of the board or a single side, but if you use both sides of the board, technically it does increase manufacturing cost because you basically have to send your board through the soldering machine twice, which, doubles the time it takes to manufacture. Why do we use PCBs? This is a nice image from Nick Howard's summer project 2 years ago, which really shows how using a PCB changes the characteristics of your signals. So, first of all, PCBs are basically standard for most manufacturing processes, and the performance of these is typically better than breadboards due to less parasitic inductances and capacitances. These can cause ringing, so on very sharp edges, you can see that top signal has a lot of oscillations as the signal transitions from like off to on and on to off. On the bottom image, you can see that all that ringing has almost disappeared. There's still some, but it's significantly reduced. PCBs are relatively durable, being commonly manufactured on fiberglass. They're cheap to produce and allow a much higher density than manual assembly. So PCBs consist of many layers. Typically, the entire makeup of these layers is called a stack-up, and it's something we're going to have to configure today when we do our PCB design. Typically, these are classified by the number of layers. You can do single, 2, 4, 8 layers. You can go crazy, 16, 24, but typically after a single layer, everything is a multiple of 2 just because that's how they're manufactured symmetrically. They don't really make a 3-layer board that doesn't exist, and manufacturers will just ask you, why are you doing that? And there's also specific compositions that are for like tighter design tolerances. So if you're doing like RF or microwave, you're probably going to want to select something called Rogers, which is uses a special dielectric instead of just standard fiberglass. So the copper and core is the main part of the PCB. The core is typically fiberglass. It could be other materials such as FR2, polyamide, which is for flex PCBs, Teflon. Sometimes people use aluminum. I really don't know how that works, but it is a thing. And then you have 2 copper layers laminated on each side. The process that happens is like photolithography, so you basically put a photoresist, you etch away a pattern, you use acid to etch away the copper, and then you remove that photoresist, and you're left with all your patterns on the traces and basically everything that you need that makes up a circuit board. Next is the solder mask, which is a layer that goes on top of the copper after it's etched. This prevents solder from sticking to where you don't want it. So as you can see in that image, the pads or those silver parts are the parts that are exposed. Solder will stick to those. The green stuff, which basically makes up every color of the PCB, is the solder mask itself. So if you want a black board, your solder mask is black. They do make clear ones, they make pink ones, there's a lot of different colors. If you make your own board, I'll allow you to select your own color as long as it's on JLC's like standard color options. So if you're interested in getting like, I don't know, an orange board or a yellow board, that's an option. Solder masks are also patterned on very similarly to the etching. You just expose your chemicals to some light with the photo mask, and then you cure it and it becomes hard. And next are silk screens. Silk screens are basically all the white text. So you typically use these for component designators. So I neglected to go over designators in the previous week, or at least populating designators on the schematic, so that's the first thing I'm going to go over today. But on the PCB silk screen, that basically tells you where each component goes if you're doing manual assembly or debugging. You can also have additional notes, you can put logos, you can put like warning signs. So on the bottom you can see like, I put the ECE logo and IEEE logo on the reference board just so you can see how that's kind of done. Silk screens are typically only applied to the solder mask. You don't want silk screen on your copper. JLC is very nice because they will automatically clear any silk screen that will be put on top of a region that doesn't have solder mask. But some manufacturers aren't as nice and they will just print silk screen on your pads and you're gonna have problems soldering that component later. So it's just something to keep in mind. So any questions about PCBs and their composition? Alrighty. Next off, traces. Traces are basically the wires of your PCB or of a circuit. They're the primary way of connecting electrical components together, and they're covered in the solder mask, which basically acts as their insulation, so you don't have any short circuits. Typically, manufacturers will have a tolerance or a manufacturing limit of what they can produce, so make sure you adhere to that. I will provide you with a file today that will basically prevent you from creating traces that are too small to be manufactured. They will throw an error when you try and compile the board. But just know it's very different for every manufacturer. Sometimes if you do 4-layer boards, you can go thinner. Some manufacturers like Oshpark is not as great as JLC just because their manufacturing node isn't as capable. One thing that you do have to note about traces is their current capacity is dependent on the weight of the copper and the width of the trace. So copper weight is basically a measure of how much copper is distributed over 1 square foot. So you'll see like 2 ounce means 2 ounces of copper distributed over a square foot is the weight of that copper or the weight of that PCB. We will be using 1 ounce just because that's the most common. 2 ounces typically for high current boards. If you do need more high current capacity, you typically just widen the trace and it should just be fine as long as you don't have any weird requirements or manufacturing defects. The other way to connect things are planes. So planes are, instead of just a line, it's more like a region. So these are typically good for power and ground distribution. So on multi-layer boards, you'll typically see like the center board will either be a ground plane or a power plane. This allows components to get like a very clean power signal or power supply, so you don't have any like noise or any weird RF or operation modes that you typically didn't expect when you were manufacturing at the start. So at the top, you can kind of see that green region surrounding all those purple things. Those purple things are traces. The green is all planes. On the bottom, you can see, this is actually from the reference design. I use a lot more planes than traces on the board itself, just because I like to have the capability to draw much wider traces and vary their width as the path travels. Just because traces, if you use a standard width and you try and increase it, it kind of creates these weird shapes. Planes are a little bit more configurable. You can round the edges. You can basically draw it how you like. There are special considerations for planes. You need to remove things called islands and necks. Islands are basically regions of disconnected copper. So sometimes it'll generate, and then you'll have like a little square of copper just floating in the middle of your board or in the middle of some traces that's not connected to anything. That is bad. That can act as a resonator or some other defect, and that's just not something you want to do. So you remove those typically. Necks are also really thin regions of the plane that are either thinner than can be manufactured or will not be able to hold the current capacity that you're really aiming for. We also have thermal reliefs, which I'll go over more when we talk about pads, but that's just something that can be configured when you have planes. Next, we have vias and drills. Vias are basically, oh yeah.
Sorry, on the planes, if you say it's like an island,
Yep.
how do you get rid of that island? Can you just like connect, like if it's like a ground plane, and there's like an island of ground that's not connected at all,
Yep.
can you just connect a single or a single trace?
You can, yes. So there's multiple ways of getting around, yeah, so there's multiple ways of getting around islands. Sometimes if you have a ground plane, for instance, you can use something called via stitching, which if you have a ground plane on your top and your bottom layer, you'll put a bunch of vias, which I'm going to talk about next, but they're basically connections between the top and bottom layers, and that will electrically connect it to ground. Sometimes if you have a region that you just can't do a proper via to, you can draw a trace to it and it will be connected.
Will it like resonate or anything?
It could be bad, it could be a resonator, just because if you've heard of things called patch antennas, those are resonators. They're literally just like a square that's specifically designed to resonate at a certain frequency. So typically you want to avoid islands in general. Sometimes they're unavoidable, but usually you can just remove them and not really have to deal with them. Does that answer your question?
Yeah, thanks.
Perfect. Yeah.
Why, like, what is a resonator and why is it bad?
So there are certain things, it's EMC and EMI, so electromagnetic interference and compliance. If you have a resonator on your board and you have like an external signal, it could make that oscillate. And if you have other digital or analog traces running nearby, they could pick up that signal. And let's say you have an ADC, so you're measuring an analog signal. If you have a resonator or something that's oscillating on your board near that specific node, you're going to detect that resonance, which you probably don't want because that's not what you're measuring. So typically, for electromagnetic interference and compliance, you typically remove these just because you don't want these unexpected signals interfering with the operation of your board. So does that make sense?
Yes, thank you.
Perfect. Any other questions before I hop onto vias? Perfect. So vias and drills. So vias are basically the holes that are used to connect layers of the different PCBs. Since we're using a 2-layer board, the only via you're going to see is the through via, which goes from the top and bottom holes, which you can see there's 2 of them on that cross-section diagram over there. I do recommend when you're routing to minimize the use of vias on your signal traces, just because vias have different characteristic impedances than your traces, so it kind of influences your signal a little bit. They don't have as high current capacity sometimes, so you have to stack multiple vias, but if you can, avoid using vias when possible. There's other types of vias you can see. There's like blind vias and buried vias, which are those 2 in the middle, which we won't be using, but those are for multi-layer boards. Those are basically vias that are drilled before you put the extra layers on, and then you can't actually access them afterwards. But they're typically used to connect like your 2 inner layers or your top layer to another inner layer. There's also holes. Holes are good for mounting points. You can have non-plated or plated vias. Depending on what you want to achieve, sometimes you want a plated via that's connected to your ground plane, so you can ground your board to the chassis. Sometimes you don't want that because it's a high voltage board, so you can set that as non-plated and you don't have any ring around it. So those 2 have rings, you can remove that entirely so you don't have it. Next are pads. Pads are basically the exposed copper that the components are going to be soldered to. These are not covered in solder mask, and they can either be through hole or surface mount. They'll refer to the same thing. Really depends on the component. So pads for surface mount components are single layer. Through hole is a hole that goes through the board. So like that resistor over there has a through hole pad. The pads are pretty important to get right. If you look at data sheets, they'll typically have a recommended footprint layout. And a lot of them are standardized. So I'm going to talk about components because that segues right into there. So footprints are the arrangement of the pads that are used to attach components to the PCB. You can see like over there, it's kind of difficult to tell, but different components or the manufacturer will recommend a footprint that you put on your PCB when you're assembling or when you're designing. So you can see like all the different widths of the pads, all the different pads that are present on the chip itself. These are all things that you'll either create or have a like schematics or another tool help generate for you. Make sure that you select the correct footprint for the component that you're using, and make sure your pins map correctly to the component, because if you have two signals switched, your chip's not going to work. There are standard component sizes. So for resistors, those are typically like 0805, 0603, 0402, there's 0201. There's a bunch of sizes out there that you typically won't use as a hobbyist. You'll typically stick to like 0805, which is what we're going to use just because it's easy for us to solder, especially as not many of you have gotten surface mount soldering experience. So something to start with is 0805. Moving on, you can use 0603, which are what I use on hand, and 0402 is something that I would say is about the limit of what you can comfortably solder by hand. Beyond that, you typically use a stencil and a pick-and-place machine sometimes. There's also for integrated circuits, ICs, you have DIP, TSOP, and QFN. These all stand for things. Like DIP is dual inline package, TSSOP is something, I don't actually know. QFN is like quad something. But these standard packages are defined by organizations out there, like I think IPC is one of them. And these are things that you will see a lot, especially when you're shopping for different components. You can select the package type. It'll say like DO214 for a diode outline type 214. That's the diode footprint that you're going to need to map onto your board. So it's just a form factor to get familiar with if you're going to be designing boards for any different projects. So any questions about any of that? Nope. Alrighty. So next are footprint libraries. So we went over schematic libraries or schematic symbol libraries last week. I'm not going to go over footprint libraries today. I'm going to go over them next week. I'm just going to allow you to import the one that I have already prepared. So they're very similar to component libraries, but they only contain footprints. It can be used across multiple files. Schematics is a great resource to getting a lot of the footprints, because footprints are honestly one of the most time-consuming parts of creating components. And these are typically under the PCB library or PCB lib file on Altium. So if you see any of that, it's typically a footprint library. So yeah, any questions about footprints, pads, traces, current capacity, planes? All good? Alrighty. I'm going to go over some brief layout tips before we open Altium. So just remember, the PCB is a physical representation of your circuit. Placement does matter. So I said in the schematic layout, you really could put whatever the hell you wanted, wherever you wanted, as long as it's electrically connected. This time you really can't. Everything matters. Avoid weaving signals with vias. This means going from the top and bottom layer with vias over and over again. It's pretty bad for signal integrity. It can produce extra noise and reflections in your signal, especially if it's a high-speed one. And power, typically you want those on a single plane or in a single continuous trace that's pretty wide so your power distribution doesn't get damaged. This is not too relevant to the design we're doing today or for this workshop, but digital and analog traces shouldn't be routed next to each other in parallel. This is because the sharp edges of a digital signal will excite the analog trace. Due to the capacitive and inductive coupling between the two traces, some of that signal will transfer, some of the energy will transfer into the analog signal. You really don't want that to happen. And then another thing that's more relevant to us is ensure that your traces will be able to handle the current capacity that you're targeting. The board that we're designing for, I believe, can go up to 3 amps. So you need to make sure your traces and all the widths of your all the widths of the power paths will be able to handle that current comfortably. I would also recommend take your time. Like, there's no rush. Well, meet the deadline, but there's no rush in creating a board that you really aren't proud of. So I think that board on the right has some good examples of how you should align things. So those surface mount resistors are aligned together. It's very nice. Things are parallel. You're using everything basically sparingly, if that makes sense. there's a logical flow to things, so things that are supposed to be together are together. So something like decoupling capacitors, which we have, I think, a couple of in our design. Decoupling capacitors are basically used to stabilize the local power rail for a device. These need to be placed physically close to the device that they're decoupling. If they aren't, they're basically worthless. Avoid 90-degree turns. This was an old rule of thumb back in the day. The reason for it was if you had a 90-degree turn in one of your traces, there's something called an acid trap. So the acid that would etch away the copper would get stuck in that corner and etch it to something that's not a 90-degree angle. Most modern processes today can deal with it. But the other reason you avoid 90-degree turns is reflections. So if you have like a signal traveling through a trace, that 90-degree bend will cause a significant impedance change when it's going around that bend and causes reflections in your signal, which typically isn't desired. And also label. So I mentioned earlier with the silk screen, you can leave notes, you can leave graphics, you can leave like whatever you want on the silk screen as long as it's not on a pad. These are very useful, especially as you move on to different projects. You might forget, okay, what voltage does this thing take? Put 12 volt in. You can put the polarity on connectors. You can label each individual output. It's just something to keep in mind. So any questions about the layout tips? Yes?
I might be just like a little bit confused, but if we're building a buck converter where we got like, we're going DC to DC, why are we, like it seems like a lot of the tips you're giving are for like high frequency, like short wavelength type signals.
Yeah.
Can you just, like, is that just like?
This is general, yeah. So because our board isn't digital, we don't really have to deal with many of those. The main thing you're going to be dealing with is current capacity. There are two nodes that are switching nodes. Those ones are kind of high frequency, about maybe, I think it's 100 kilohertz. So those ones you do want to route pretty nicely on your board. The reference board isn't the best example of it, but the supply still works. But these are more general layout tips. So as you move beyond this workshop and start doing your own boards, maybe if you have a microcontroller or you have more ADCs or have like sensors or something, these are the things that you'd probably want to keep in mind as you're going through that project. So does that answer your question?
Yeah, thank you.
Yep.
What if traces split? It seems you couldn't avoid a 90-degree turn in that case.
Traces splitting, yeah, sometimes I integrate the split in a component so it terminates in another component and then you pull off of it. Sometimes it's just unavoidable and you just leave a 90-degree bend. Sometimes you can try and minimize it by having, it's easier to draw. That's a very dead marker. Sometimes I do this, so you only have one 90-degree instead of two if you did a traditional T. Sometimes if you know where your signal is being source and like your source and destination, sometimes like this will be your source and these two will be destinations if this is a signal propagating that way. But this is an option. This is typically okay unless you're doing like high frequency, like really high frequency stuff. This shouldn't matter too much. Something I would not recommend doing is something like this. This is even worse than a 90-degree bend. I don't know, if you do this, I will reject your board, I'm sorry. It's just not good practice to have any of these. These might be problematic for manufacturing, and these are pretty awful for reflections as well, just because it does weird things to the width of the trace as it travels through. So, does that answer your question, Nick? Nice. All right. Any other questions before I talk about some project information? All good? Alrighty. So just before we open Altium, so I'm going to go over the majority of the setup for the PCB. If you haven't finished the schematic, I haven't finished my own schematic for the workshop, but I will show you how to import the schematic reference into our project. The one thing that I will recommend, even though this is your own board, there is one dimension that I'd like you to keep consistent, which is, if you can see that red on the side of the top image, which is basically the width of those two. I can walk over. Like this, these and those. Those fit into a breadboard, so you can actually do something kind of like this instead of, messing around with DuPont connectors, because those are quite frankly pretty weak and don't have the best current capacity. So that's the only restriction I have. You can add more components if you want to add like more LEDs or modify your own board. So you can. The only limit is we won't be able to provide like that many extra components. Unless it's like a component we already have, we won't be able to provide like a custom component. So any questions before we open Altium? Yes?
Were you talking about the green things that we would keep?
Sorry?
Were you talking about the green things that we would keep?
No, it's these, you can't really see them, but there's, so right here, there's a pin header. You're gonna populate, I don't have a mark, place to draw. The pin headers go down instead of up, and they're gonna be able to be inserted into a breadboard. So that's why it's a critical dimension. But beyond that, you can go wild. As long as it's within a 10 by 10 centimeter restriction of JLC as well. So, yeah. Any other questions? Alrighty, let's open Altium then. Okay. How many of you have finished your own schematic sheet? Good job.
I started today.
You started today. All right. If you haven't, I'm going to show you how to import the new one. I'm going to do that right now because I don't have one. So, if you have the GitHub, make sure you pull down the latest one. It should have the most updated files. And, in the master, you can either pull from week 3, but I recommend going to the master design reference files, going to the Altium PSU project, and taking this schematic doc, copying that, Control C, and then go to wherever your project is stored. And then you can paste that in. And then once you've done that, you can double click or right click on the project itself, add existing to project, click on the schematic document, and there you go. Now I have it. If you have done your own schematic, great job. More cookies for you. And then I'm going to go over one concept, which is annotation, just before we get into actual PCB layout. So everyone good? Anyone stuck? Good? Perfect. Okay. I'm going to talk about annotation, which is basically all these symbols. When you were placing them on your own, it probably said something like R question mark, which that's not going to fly on a PCB. So what you're going to do is under tools, there's annotation and annotate schematics. And this opens up this window, which is really nice. And there's a lot of information in here that I really don't need right now. But this is where you're going to be annotating your schematic. So I'm going to reset all of these. So if you had a blank schematic, all of the schematic symbols, let me just do that. See, I'm getting errors like you have duplicate names, but all of the symbols are named R question mark, L question mark, U question mark, which is not great. So we got to annotate. So we're going to use the annotation tool, annotate schematics. You click update changes list, and that will propose new designators for every component. And the way it does it is if you look at the left, you can see how it assigns like R1 is the top left corner, R2 is going to be directly to the right, and then as you go down, you increase to the next value. You can change this. You can do like, this mouse doesn't like me, like that. I typically like the default. It works well enough. But yeah, since this is a single board, it's pretty simple to annotate. You might have like multiple sheets down here, but since we don't, we can just press update changes and then accept changes, create ECO. Does anyone know what an ECO is? Nick.
It's in the other side, it's engineering change order.
Correct. Yep, engineering change order. So it's basically take all my changes and do it. And then you can have it generate a report. We don't need it. There are 3 buttons here. There's validate, execute, and report. Validate will make sure you can actually do everything. Execute will do it. Altium will allow you to just click execute as well, but it will tell you if any of the changes were not able to be done. But yeah, once you do that, everything should be annotated. Yes.
You should look at the annotate schematics quietly tool.
That is also an option. If I here, let me nuke an identifier.
Just Control Z till they disappear.
Oh no, my laptop is doing a. Oh dear.
See ya.
Hi. You are not real.
Yeah, you just Control Z till they all vanish.
Annotate. Where is it? Quietly. This one.
Annotate schematics quietly.
Yeah, and then it'll annotate.
And that just does the default.
Yeah.
You already-
Yes.
I'm sorry, I missed the part, after you went to annotate schematic.
Yes.
How did you get to like the execute part?
Okay, so from here, I'm gonna reset all and then update changes. There's this button that appears, accept changes, create ECO. And then you click on that and then validate, execute, and that'll annotate your schematic. Yep. And then I'm going to re-annotate everything because I clicked. Alrighty. Any questions about annotation? Alrighty. So now I'm going to make sure we have the footprint libraries. So we're going to do a similar process as we did to import that schematic sheet. We're going to go to the GitHub repository. This time, instead of using the reference Altium PSU, we're going to go to the component library, USB-C power supply, and just take the PCB-lib and the schematic library, and then copy those into your, that's not right, into your directory. And then you're going to add existing to project, just like before, and select those 2 and open those. And you should get another folder with libraries in it. If you completed your schematic and you already had the reference to the schematic library, that should already be present, but the new one should be the PCB library. And if you want to open that up and just like take a gander, sneak peek at what we're going to do next week, or what I'm going to cover next week, it's stuff like this. These are what your components actually look like before you put them down on your PCB. And then I'm going to save all of this. So yeah, anyone having trouble importing libraries? Alrighty, so if you want to import like an Altium library footprint, you can go, I think it's manage.
Manage?
Yep, and then plus.
I do the file.
You do the file,
The file.
yeah, and then you can
Wherever
wherever it is. Component library, this one. Select folder. And then you can change the file type to Altium Designer. And then you can, I think you can just, oh no, don't do that. You can find the file itself. Like that. Open it. And that will add it to your design library. I don't actually want to add that one because I have one. Alrighty. Any other questions before we move on to actually making a board or starting our board? Perfect. Alrighty. So I'm going to create a PCB. I'm going to right click, add new to project, PCB. And that should just generate me a PCB if my laptop wants to load. Oh, there you go. Nice. All right, so that created this PCB project or project file. I'm going to rename it right now so I can force save it. I'm going to call it USB-C Power supply. And then I like to just tack on PCB at the end for fun. And save that. And this is your blank PCB. Some basic controls that I'm going to go over are how you navigate. I'm using a mouse, so left or right click is how you click and drag your position. Scroll wheel is up and down. You can hit control scroll wheel, go in and out like that. You can also use like 2-finger on your trackpad, but I recommend please use a mouse. This step is pretty hard without a mouse. You can do middle mouse wheel to zoom in and out as well. And then some of the stuff at the top there's also the same selection filter as we had before on the schematic creation tool, and a couple other selection tools. There's an alignment tool, same as the schematic as well. There's place component. See, this one's an interesting one. I typically don't recommend going from PCB to schematic when placing components. I recommend placing your component on your schematic first and then porting it over to your PCB. You get a lot of weird design rule errors that I just don't want you to deal with. There's traces. There's multiple different trace routing modes. So like interactive differential pair, which is for like USB, or if you have any other differential signals. HDMI, I think, has some differential on there. Quick routing, quick differential pair routing. Those ones are just slightly different. The ones you're probably going to use most is interactive routing tool. And there's also interactive multi-routing. So you'll select multiple signals, and you basically create like multiple parallel traces to each other. So if you have a bus or like just a lot of signals that are related to each other, you can route them all at once. There's also length tuning. This is not something we need to care about, but if you have like digital signals that have a propagation tolerance, you will need to tune those. Vias and holes, or vias and pads, don't call them holes. This is another thing you're going to be using a lot. You can place vias like that. And then there's polygons. The one that you're going to probably use the most is the polygon pour. This is how we make regions. So you can draw it out. You can make really weird ones. You notice as I moved it around, it disappeared. I will go over why that happens and how to fix it. There's also other like cutouts and regions that you don't want to pour. There's these other tools. I'm not really too familiar with those. You can add text. So you can see I had something in here from 2024 that I last typed. And also you have a bunch of the line tools, the same as the schematics. Everything's still on a grid. However, it is not the 100 mil grid. It is something different. You can choose what grid you use. I am a metric man, so I typically like to use 0.1 millimeter. I press G. Nick, I know you're imperial. I'm sorry. But this just changes your snapping, I think. You can do grid properties as well. So I type in 0.01. I'll show you how to do that quicker. But anyways, the first thing that we're going to do is we're going to set up the stack up. So remember on the slides I told you that's basically the makeup of our board. What we're going to have to do is we're going to have to change to the PCB shape form, or menu, layout, view. You click one, you click on the number 1 on your keyboard, and you get this. This is the shape of your board. This is also how you're going to redefine board shape, but first we're going to do stack up. So under design, there is define or layer stack manager. And you're going to click on that, and you'll get another menu that pops up. You can just close that one. And here is basically all the different measurements of your PCB, the characteristics. The one that we have to change is the core. So JLC PCB, we're going to be manufacturing 1.6 millimeter thick boards. I don't know the exact thickness, but you can put in 1.6 millimeters for that parameter, and that changes the dielectric FR4 to be 1.6 millimeters. I'm still in imperial, but you can type in the dimensions 1.6 mm, and it'll automatically convert it for you. There's other stuff in here. So if you have a multi-layer board, this is how you define more layers than just the basic 2. So you have this button add. You can add like signal, plane, core, all of this stuff. And it'll put, more layers on your board. I don't want to do that because we're doing a 2-layer board, but that's just something to know if you design more complex boards, such as like Will's temperature monitoring. His circuit is a 4-layer.
Our graphics card with like 14.
Okay, we're not designing a graphics card. You can go work for NVIDIA.
Trivial, bro.
Don't say that word to me. All right, so that's the layer stack up. You can close out of that. And then this is the shape of our board. Typically, I am fine starting with this because I don't have a specific size in mind. But I'm going to show you right now how to change that, how to change the size of this board. So under design, you can either redefine board shape, which will give you basically a free layout tool. So you can make the wildest board shape you want. There are restrictions to what you can or what manufacturers are okay with manufacturing. This would be an example of what they would probably look at you and say why, but some manufacturers would just try it anyways.
JLC would go for it.
JLC would go for it. JLC's made some weird stuff. They're also fun. Yeah, that's why I like JLC.
They just want the money.
They want our money. They're probably training some AI off our boards or something, but don't send anything ITAR to them, please. That stays in the US or your company. Please don't, just don't. But I'm going to define this more reasonably. So I'm going to do under design, redefine board shape. So, hold on. I need to change this menu in the top is the overlay, or I think it's called the overlay. I prefer millimeters. You can use imperial. To change the measurement, you press Q. So I'm going to stick in millimeters. I'm going to make my board like 5 by 10, just for a demonstration. So I'm going to redefine board shape. I'm going to align my cursor with the origin just to make it easier. And I click on it, and you can see that top, this little thing up here has my cursor coordinates and also a dx and dy. Dx and dy are basically the change in your x and your change in your y since your last click. So you can basically measure things. So if I want 5 millimeter or 5 centimeters up, that's 50 millimeters in the dy direction. So I have 50, and I just click. And I can go 100 in the x. So, and to make sure I'm not, going up or down, so this is up, down. To make sure I'm actually on point, you can look at the dy and make sure that's zeroed, and click at 100. You can also manually modify these points if you do need to edit them later, but you don't typically. And the other reason why I use the origin is because I can just scroll all the way down. It'll snap. I won't have to fiddle with another coordinate. I just have to stay vertical. I need to be directly under the last point I click. So we click that, right click to exit, and there's my board. One thing I do after this is I'm going to move it away from the origin. So I'm going to do design, move board, and move it a little bit. And it's asking for me for the board region. We're just using the default. So yeah. So that's the gist of it. This is where you can do like rounded boards. You can do other shapes if you want. This is typically not where you do slots. If you're doing high voltage and you need creepage isolation, this is not where you would drill, where you indicate your slots. That's something you would do in your schematic editor or in your layout editor. So, anyone, yeah.
How do I move my board?
In design, move board. And there's two things in there. There's move board shape and move board. Move board will move your board and all the components that are currently on it. We don't have anything, so you really can't tell the difference. But move board shape will only move the board itself. Your components and your traces and everything else stay in place. So make sure you know what you want to do before you click it. There is Control Z, but I said Z, yes. Z.
It's American.
I'm using the metric right here. We're in no man's land. All right, so to get back to the main layout editor, you're going to click 2, and now you should see that, that green region turn into where your board is. There is one more region, or one more layout that I would like to show right now, just because it's kind of relevant, is 3. 3 is your 3D viewer. So you can see that this is a board. You can hold shift and you'll get this thing. Globe? I don't know. And then you can manipulate it with your right click, and you can like view your stuff. If you have 3D models assigned to your components, you will be able to view them on this board, which is how I got, the renders for the PowerPoint. So like stuff like this. Those are all 3D models. Semaxis typically has 3D models. Another reason why I recommend looking into it. 3D models take a while unless you're really good at 3D graphics for some reason. I won't judge. So here we're going to import our components because right now it's blank. We need to make sure we have all of these symbols done. One thing that I will show right now is I've already assigned all the footprints to these components. If you looked at your symbol library that we have, you can see that each component is already assigned to a footprint. I will go over like doing that process next week. But one tool I would like to show you is the footprint manager. So under tools, footprint manager, this will give you a list of every single component that's on your board and the footprint that's currently assigned to them. So if you have like, this is the trimmer potentiometer that's on the board. The footprint that it's currently assigned to is this one right here, which is a little bit funny and we'll talk about it later. But to make sure all of these components are actually found and will actually be populated on your PCB, I usually do a sanity check and I select all by Control A, and then you can Control A on the second window that opened up and click validate. And it should say found in and then the library that we imported. This means that it knows what footprint it's going to pull, because sometimes if you have a footprint that's named a certain way and it links it to another library, your footprint's going to be different. So this one tells me that every footprint that I have is going to be tied to the library that I just imported, the footprint library. So those should all be correct for you. If you have issues with that, we can talk about it. It should just work, hopefully. But once all those are validated, we can go back to the PCB and we know all our symbols are assigned to a component footprint. We can go design, import changes, and this will generate, or this will show the same engineering change order as we saw before. So you can validate, it'll give you all check marks and execute. If anything failed, these wouldn't be green, you'd see a red. And that's where, oh shoot, I gotta check something again. But once that's done, and you can close out of that, you have all these footprints that we will now need to place on this board. That's going to be the hardest part and will take the most time. So moving components is basically the same as symbols. I would reference the design that we have already provided just for some guidance on where things are typically located or how we're arranging things. So like the input side is on one side and the output on another. So we typically group everything that's related to each other. So I'm just going to go, one more thing before we start routing is design rules. Did you have a question?
Yeah, did you just do validate and execute?
Validate, execute, yep. And it should just let it go. So one thing you'll notice is, hey, the default rules are telling me that my hole is an error. That shouldn't be. JLC will happily drill this hole. There are something called design rules that we can basically modify to make sure that our design is manufacturable. I have provided a rules file in the GitHub so you don't have to create your own because they kind of suck to make. So if you go to the repository and go to the component library, it really shouldn't be in here, but there's this jlc rules.rule file. this file has all the different rules that we'll need to make sure that the traces will still be compliant with JLC and you won't get weird errors like this component freaking out. So what you're going to do is you're going to go to Tools, or what is it? In Design and then Rules. And then what you're going to do is you're going to right click on this window and import rules. And it's going to say like, okay, what rules do you want to change? I'm going to use all of them. I'm going to overwrite the entire thing with the rules that I have provided. So you can Control A, press OK, and you're going to need to search for that rules file, which will be in the master design reference, Altium component library, JLC rules.rule, .rule. Open that. You're going to clear all the Altium defaults, and you can close out of that window. Oh, hi. Oh, it's still erroring. Those shouldn't error. Ignore those. Those are the heat sinks. I'll fix the rules file. You can clear error markers by doing T for tools, or you can go up here and reset error markers. But yeah. Yes?
I missed where you went at the very start to import the
That's in the, design rules. Right click on this left window, import. Control A on all of them, press OK. And then you can go to the GitHub and under master design reference files and an Altium component library, click on that rules file that is there, open that up, clear all your existing ones, and press OK, and then you should be good. I think there's a 3D issue with the 3D model. That's probably why that's erroring. I'll fix that. But yeah, anyone else have any issues with importing those rules? Nope. Okay, so I'm just going to go over some of the basic stuff to draw traces and planes, and then you should be good to go start doing layout. It's not too bad. So on the bottom, there's a couple different, quite a few tabs. The ones that are going to be most relevant to you are going to be top and bottom layer, and the top overlay and bottom overlay. These are the top and bottom copper and silkscreen layers. The top layer is typically red for the top copper layer, and the bottom is blue. This is pretty common amongst PCB softwares. I think most of them use red and blue as their top and bottom copper layers. And then their internal copper, those are non-standard. Some people like funny things. But there's a lot of irrelevant stuff in here, like drill drawing, keep out layer, drill guide. We're not going to really be messing with those. So under the left window, you should have a view configuration little tab. Under that, we're going to remove the mechanical layer, or not the mechanical layers, the other layers, because those really aren't relevant to us. I would leave the other ones on because those indicate like keep out regions and also where the 3D model is located physically on the component. Because if you look in the 3D view, look, we have components. Those heat sinks are not green, those are black. They are black. All right. And to edit the different layers, you just need to select which layer you're on in the bottom. So we're going to just stay mostly in the top copper layer because that's where all our components are. I do recommend trying to get all your components on the top rather than putting some on the bottom. Even though you're going to be hand assembling these, it's just something to simplify the assembly process. But I'm just going to start with the input side. So if you look at every component, there's its designator. And if you refer back to the schematic, the designators for the input were J1, J3, M1, and J4. So I'm going to look back at my PCB, and I'm going to find those. So J4, M1, J3, and J1. So these are all our different inputs. And as you can see, it's a barrel jack, 2 terminal blocks, and the USB breakout board. So I'm going to arrange these at this edge. You can choose however you want to arrange these, but if you need a reference, please use the reference. It is a pretty compact layout that's not too bad to use. You place these here. You can press space to rotate just like the schematic editor. And then we're going to draw some traces just to show you how that works. I'm going to connect all the V and A's. So you can see I'm highlighting over this trace. These are ghost wires. These are basically showing every connection that needs to be made. So there's this whole mess of connections that are not currently being done. Those are things we're going to have to do. So I'm going to click on the trace tool and just click one, connect it to the other. Very nice and simple. You can drag these around and it'll try to reroute them as best as possible. You can delete different sections if you want to redraw just like a particular node. You can press space to change how it bends around a corner. And if you want, you can go to properties, and you can go, the properties window by pressing tab, just like the schematic editor. You can change the width. So I'm going to change these to like 1 millimeter, and it changes it to 1 millimeter. One useful thing about Altium is I think it will tell you the current capacity of this trace. So if I place it down and press properties, does it show? It's not showing. Oh, here. Under show more, you can see max current. So this trace, this 1 millimeter trace, with the current settings we have in the stack up, will allow us to do about 3.2 amps. That's with a 20 degree centigrade temperature rise. Typically, I size these almost double. Depends on your design. Sometimes it's okay to have that high of a degree of temperature rise, but I usually double it for this board especially because it does get hot. It is a switching regulator. So that's how you draw traces. The other thing is planes. So I used a lot of planes on my board. Is you can draw it around each component that you want to, or each pad that you would like to connect. And it will draw this copper region. This copper region is not really connecting to the component or the pads that I wanted it to. It forms this like little barrier around it. The issue is this pad is not assigned to the net. Every component will have a net. That's why all these guide wires are floating. They are trying to connect to the same net. So you're going to go properties. You're going to go net. And you can technically type in it manually. I use the eyedropper tool. And I can select that. And it disappears. This means that the pad has been, or the plane has been updated and is ready to be redrawn. To redraw it, it's under tool or, oh, no. Yeah. So it's under tools, polygon pores, and then repore all, and that will redraw this polygon in order to draw it. And this will put these little connections. These are called thermal reliefs. Thermal reliefs are decently important, especially for hand assembly, because a plane is just a big copper heatsink. Like, if you have no thermal relief, so I can turn off the thermal relief on this pad by selecting it, going down to these settings. Soldering's going to be a pain. Ask me how I know. So you can do direct connect, and then you redraw it. This pad is connected directly to this copper plane. You're going to have to heat this entire copper plane to the temperature that your solder melts at in order to solder this pin. It's bad. Don't do it. Especially if you have a heat sink. Don't. It's such a pain. But you notice these are a little bit thin. I'm going to increase that. So under that same window, I click on the pad, go to properties. You can see there's the copper and then the thermal relief. You'll need to check that, and then you'll see relief connect. You can set the conductor width. So I'm going to set this to like 0.5 millimeters. Press enter, and then I need to redraw that polygon. The shortcut that I use, and I use a lot, is TGA, and then it just redraws it to be slightly thicker. So yeah, those are the main connections that you'll need to do. Vias are basically just like components. You have a trace, you can click on the via, put the via on, And then now, if you go to the bottom layer, you'll see it's blue. That means this has made it through. There's copper on the bottom layer. And now you can continue on with a blue trace. And that's the main fundamentals of PCB layout. Beyond that, there are a couple extra things that I would recommend learning from the reference design, which are via stitching, which are all these tiny little holes, and ground planes. There's a huge ground plane on this board. So you see like all these small traces, and you see the main bulk of the system is on the top with planes. So like this is a plane, this is a plane. Oh. There's a couple traces, so here's a trace. Typically to low current stuff like LEDs, there's traces in between here. But via stitching is an option. If you have two ground planes, you can use, there's a tool that you can use. It's called under Tools, via stitching, add stitching to net. There's a bunch of different parameters. Once we get further on in PCB layout, I'll go over this next week just so you can actually see it. I don't have ground planes to demonstrate. But that will basically establish a very strong electrical connection between the top and bottom ground planes, so you can have a solid return path for all your current. It also technically simplifies the layout a little bit. You'll see this a lot for also thermal. If you have a component that has its heatsink bound to the PCB itself, that PCB is acting as the heatsink, and you want as much copper as possible to help dissipate that heat. So you can put copper on the top, and you can also put copper on the bottom. And to help the heat transfer between the top and bottom, you put vias. These are known more as thermal vias, they're not quite electrical vias, or not used for electrical reasons. But they're vias nonetheless. They electrically connect to two pads. And the last thing I will go over is the silk screen. So you can see all these different designators that are on the components. You can move these around however you want. On the reference design, I actually put some of them under the component because I don't like to see my designators. I am a masochist sometimes and don't put any designators on my boards and solder them manually. You just have to reference your design files a lot. But you can move these around. For text, it's just like the schematic editor. Also, you can flip. I didn't show that before, but it's Control F. You can flip your board. And then you can mirror. So this is technically mirrored because I'm on the bottom layer. Oh, don't do that. But I can do properties, don't mirror that. So I'm going to go back to the top layer, and it's correct. It's the right direction. So the silk screen, you can put lines. Typically, you don't use traces. You use basically the drawing tools, which are the two top right options in the toolbar. Traces, you can technically draw them, but it will force you back onto copper layers because there's no such thing as a silk screen trace. It's a silk screen line. So you can also draw in the copper layer. Use traces to connect things. But yeah, you can draw lines. If you want different style lines, you can hit Shift Space, and this will change, like if you want an arc, if you want a right angle, if you want to be funny with one of these. There's freeform, but typically you want to stay in the standard 45-degree bend, or the default style. You can also import images. If you do here, or no, that's under place. You can place a graphic somewhere, so you'll draw a region, and then we can have that. And then, wow, it converted it to a silkscreen object. That is actually awful. But if you have any logos or graphics that you'd like to import, like a high voltage symbol or a high temperature symbol, you can import it that way. I put funny things under some of my footprints just because if like a connector, let's say I have a connector that's surface mount. I put a sad face under it because you'll only see that if your connector rips off. So you can put little Easter eggs. I think they're really fun to see. I really enjoy when I take down a board and it's like, oh, the designer had some personality. But yeah, graphics are typically the last step don't do graphics first because you need to know where the components are going. If you don't know where the components are going, I really don't know why you're doing graphics at that point. Like, your board's not done. It's like you're eating dessert before you had dinner. Like, sure, we're all adults here, but come on. So yeah, any other questions before we wrap up? Yes. Sorry? Oh yeah, you can take a look up. And if anyone else wants to see the reference model, like a physical version, this is the closest one to the one that we're going to be making. So yeah.